P of theta, and it equals cosine squared of theta, as simple as possible for all possible values of theta. You can go from minus pi to pi, or from 0 to 2 pi. Do you all follow me? All possible, and obviously that thing's periodic with 2 pi there. So if you have that and you plot it in the linear domain, let's say this is theta, and this is pi, and this is minus pi, and you can call this minus 180 degrees, if you will, and this is going to be 180 degrees. And if you're plotting this P of theta, the way you plot any function, if it's a mathematical statement, you want to estimate what it looks like. Pick points. So at theta equals 0, what is P of theta? 1. Keep going on. Say at 30 degrees. What's the cosine of 30 degrees? Square root of 3 over 2? Somewhere out here. What is it at, say, 45 degrees? 1/2, right? Isn't it? And if you just extend that, you can see what's happening is at 90 degrees it goes to 0, and then the whole thing repeats itself. You all with me, class? The only thing I'm trying to show you, it's a cosine squared waveform, no negative values. Now, whenever you plot something in a polar domain, and this is 0 degrees, and this is 90 degrees, and this is 180 degrees. We're going to do it this way. With me? And make this minus 90, and this could also be minus 180, because plus or minus 180 is the same point. It has the exact same values in terms of the cosine squared value. So pick the point. At 0 degrees, it's 1. Then you're coming down. What you're talking about is this distance being proportional to P of n, or P normalized to theta. Then you simply do pick points down here, and you're going to see that this actually is going to make that type of a dumbbell shape. It looks just like the sine squared, only it's altered by a 90-degree shift. Now I think everybody, by this, make sure you know this, okay? You're going to get another polar plot or two, so you might as well just appreciate how to do it. And just think rationally about it. From linear, map it onto that, because now the angle is something that gives you the actual, you might say, the radial distance it'll locate on. The value of the radial distance is when you evaluate the cosine squared at that point. That's all I'm going to say. And a lot of people miss that, by the way.
I think I was used to the 0 being on the right, and then it goes, but that's...
No, 0 is usually vertical axis, z direction is 0. The horizontal direction is 90 degrees. That's almost always it. Now the truth is, for a short dipole, the sine squared is a maximum at 90 degrees, so it would have a maximum value there.
So when you said the P of theta, the power at the
That's a normalized power density.
We know this because you gave us the gain, and the gain is equal to our D max, or
Gain max times the actual what? The functional change, right? So if it's normalized, this is the normalized value of that.
yeah.
And if you didn't plot normalized, if you plot the peak value, it's still going to scale proportional. It'd still be a figure 8.
Except instead of at 1, it'd be at 3.
That's right.
Yeah.
And but that's what it would look like. With the Friese equation, what we're finding out is a ratio of just P received to P incident. That's all it is. So I'm going to come up with a problem. We're going to do it. And I'm going to ask you to think about how you would do it. These problems can have any form. So I'm going to say there's an antenna here, located, and call it at the origin right here. And this antenna, if this is the z-axis, and therefore when we take a look at a radial distance r, this would be the angle theta here. And I'm going to say for this antenna, I'm going to just leave it like that. The gain of this antenna is going to be 3 times cosine squared of theta. The actual impedance of the antenna is going to be 50 plus J20 ohms. This is the antenna. I'm just showing you where it's located. I'm going to make this at a distance of the gain. I did a good job at doing that. Make this at a distance of 1 kilometer. I'm going to put a dipole here that's going to have a length equal to 0.485 lambda. I'm going to make theta 45 degrees and make this angle 45 degrees. So if that's 45, this is 45 as well. What I want to know is, what is the maximum power received by that antenna? So I'm looking for the maximum power received, and I'm going to give you a frequency. Make the frequency be equal to 300 megahertz. All right, so these antennas are basically low gain antennas. They're not high gain. High gain is like 30, 40 dB. 20 dB is pretty high too. So I want to figure out the total amount of power received, not the amount of power that can be extracted, but total received at that. So you know, and these are in the plane of the board. There's no tilt angle where you have to take the cosine of the tilt angle and square it to worry about. Got me? So if I do this, I know P received over P transmitted. We're going to get to this in a second, and I'll show you what this, the equivalent circuit for this one, for the antenna there, would be a voltage source. And I didn't put that down there. Let's say Vs is equal to 20 volts peak, right here. So here's my voltage source. This will look just like the quiz. I'm going to say there's no source impedance, so really now I'm going to have an actual impedance that limits current of simply 50, and this would be J20, and this is the radiation resistance. I'm assuming there's no ohmic losses. Can you appreciate this? Identical to the quiz. So I'm finding this out. I'm going to put the equation down, then we're going to go ahead and get this stuff. We know for this equation, I always usually work through it. I'll find the transmitted power that we'll get to. Then from that, because I have the gain, I'll find the power density. After the power density, I find the effective aperture of that antenna. And after I have the aperture, I'll take a look at the total power received by taking the aperture times the incident power density, correct? If you want to use the formula, and the dangerous thing about this is, on tests especially, that's something coming up in a not too distant future. I will ask for the power density right here. And I'll ask for the total power received, both, not just the ratio, not just one or the other, P received and something. But for here, it's usually lambda over 4 pi r, and the whole quantity is squared. Then you multiply it by the gain of the transmitter. Now that's the gain of the transmitting antenna, but it's at theta equals 45 degrees. Then you, what? The gain of the receiving antenna. That is a dipole, half-wave dipole effectively. Even though we cut it down to 0.485, the only reason I do that is to get rid of the reactive component of the antenna impedance. So now I could say it's this times the gain of the receiving antenna. I would give this to you, is 1.64. This is for a half-wave dipole or dipole that's just under half-wave. Then it's going to be times what? Cosine of pi over 2 cosine of theta, all over the sine of theta, but this quantity is squared. Y'all follow me? Now theta is 45 degrees. I did this because it'll make the calculation easy. And this gain right here, 45 degrees, is what? Just 3 times cosine squared. Might as well put it in here. So it's really 3 times cosine squared of 45 degrees. I'm putting it all in just so you understand this. Remember that this entire quantity is squared because it's related to power. Now we'll put in, what's the wavelength for this one by one? Take a look at it. We're in free space, assume we're in air. Wavelength is C over F, which is
1 meter.
1 meter on purpose to make life easy. So now the ratio of P received to P transmitted, which we'll get to P transmitted in a second, is 1 over 4 pi, and that's 1,000 or 10 to the third. It has to be squared. Here, what is the cosine of 45, anyone? 1 over square root of 2. If we square, it's 1/2, right? So this is 3/2 on purpose. And this is 1.64, period. Now that might take a little doing. Let's see, first, sine of 45, let me do it this way. I have cosine of, I'll just call it 90 degrees. Cosine of 45 degrees is 1 over square root of 2. Better do pi over 2. Then I have over the sine of 45, and that is 1 over the square root of 2, right? But I have to square it. So here I'm going to get 2 times quantity cosine of pi over 2 square root of 2. It has to be in radians squared. So can you tell me what that angular function is? 0.39. Okay. Now, come down here, 0.39, and I'm assuming you guys are. So what is this ratio of P received to P transmit?
It's 6.14 times 10 to the negative.
1.4. Now, we're going to get P received, but first thing, and make sure everybody knows this, I need the transmitted power, right? And you guys know how to do this. The key is what? Getting the current value. There's no source resistance. The only thing you need to do to get the current value here in magnitude only is going to be Vs, right? Divided by magnitude of Z antenna. And for us, Vs is equal to 20 over, and it would be the magnitude of 50 plus J20.
3714 at an angle of negative 21.
And I don't even care about the angle, that would be amps. All right, now, some people did have a problem with this. The total power radiated is related to the radiation resistance, which is this 50 ohm. It's the real component of the antenna impedance if there are no losses specified. Agreed, class? So now to get the total power radiated or transmitted, either one is. So P transmitted would be equal to 1/2 magnitude of that I squared times 50, which is the radiation resistance. And what do you get for that? 3.45 watts. To get P received, the only thing I need to do, and this is the total power received, not the power that you can extract. Remember, the best we can do is get half of this to a load. That's going to be equal to simply that power, which is 3.45 watts, times this factor, which is 6.14 times 10 to the minus 9, and that would be in watts. And I don't even know what that is. 21.2 nanowatts. Okay. So now what we're going to do is say, suppose I put a load onto that antenna. How would I go about figuring out what current and voltage would be across that load? You follow me? So I'm going to show you the equivalent circuit for this thing. When we have an antenna as such, and we know that it's receiving a certain amount of power, so we're going to know what that is. We know the received power. But we want to model for, how do you model that thing if that's the total received power? You follow me? So the way you do it is you say, well, we're going to model this antenna because this looks like a voltage source. We're going to put a load out here, and I'll explain to you what goes on. And we would like to know the voltage at the load, and we'd like to know the current at the load, which makes reasonable sense. So the way it's done, and it's not explained in detail in the book, this is a neat proof, and it's by something called reciprocity. In graduate school you do this stuff. Down here they can just give you the kind of the final result. So you're going to say you're going to have an open circuit voltage. That means that if there's no load connected to this thing, what would that be? So if you had just an antenna like this, and it had so much P received coming in, what would the actual plus to minus VOC be there if there's nothing attached? Remember in circuits, you always, if you want to calculate Thevenin equivalent, you always measured the open circuit voltage. Then you measured the impedance looking back at stuff. Remember that? All right, now, then what you do, now this is just the antenna, you have to put the antenna impedance here. So there'll be a radiation resistance of the antenna, plus or minus Jx of the antenna. That would be the reactance. And I'll explain this in a second. And this would be the actual lumped element model of that antenna. Got me? Now you're going to put a load on it. Here's the external. So here's plus to minus VL. And you're going to put a load on it. But the load you're going to put on, in order so we can obtain the V open circuit, is going to be the load that will allow the maximum amount of power to be extracted. Follow me? Do you remember back when you had circuits, if you had a series impedance with a voltage source, and you wanted to put a load on there, or better yet, let me say this, if you had a load and you wanted to put a series impedance that would maximize the power to load for a given voltage source, do you remember how to do that? It's always the conjugate of the series impedance of the source. So if you come down here and you say that now what I'm going to do is put on, if this is ZL right here, this will be ZL conjugated, and that would be just R rad minus JX antenna, right? So the imaginary parts would cancel if you add them in series. Does this make sense to everybody?
Is this why it's always half?
You're getting there, yeah. Exactly half the power would be re-radiated and half the power would be allowed to be absorbed if it's a matched load, only if it's a matched load. So now coming down to this, if I wanted to figure out what the actual current was there, let's do it that way. Look, the reactive components cancel, so here's what I'm left with. I have an open circuit voltage, that's what I want. But I know what I really have here is simply 2 times the radiation resistance, call it rad, that's what's limiting current. This current here, therefore, would be VOC, right, over 2R rad. Do you all agree with that? And that would be the current. Everybody with me?
So starting from the start, we have a receiving antenna. Then you want to know the voltage, so you drew a...
I haven't equated the P received yet to anything.
Well, yeah, I know, but like you have that antenna, it's receiving a signal, and then you want a voltage that's going across that antenna.
Well, if you just take that load away, this is what you have, right?
Yeah.
So there's going to be a voltage developed.
Oh, okay.
That's the open circuit. There's no current possible
Yeah.
if it's open circuit. We're going to get that in a second, but first I got to get the model.
All right.
So y'all agree that would be the current if you had matched conditions, and this is how the whole thing, the assumption of everything. Now if that's the current, I want you to think about this. How much power is being consumed by this circuit? Well, the actual power, right, would be the received power. That received power would be 1/2, right? And it would be times, now it would be I squared, I'll put it down, 2 times I squared, but then the resistance would be 2R rad, if you look at it. You follow me? You got 2R rad there. That would be the total consumed power. I'm going to go ahead and put in for I. You see these 2's cancel, by the way? Now I have I squared, so I have VOC squared over 4R rad squared. That's equal to I squared. And that's times R rad. We're going to solve for the open circuit. That's my key. Is everybody with me to this point? You can see this R rad cancels one of them, if you look. And you have this, agreed? And here's the real thing. Make sure you understand this. When I want to find out what V open circuit is, which is the key that will allow you to solve for any given load, you find out that V open circuit is equal to the square root of 4 times the received power times R rad. And that has nothing to do with the reactive value of the antenna impedance. So you get P received coming in, right through the antenna. Now, I'd like to be able to figure out how much voltage and power would I get out with a given load, right? Just remember, I cut that antenna down to 0.485 lambda last time, right?
Yeah.
And we calculated P received, didn't we? All right, now what I'm going to do is figure out how much power, and this is a classic problem. I give this problem almost every class, every 3320, and I won't give the same antennas, the same exact concept. You'll have to figure out things. And I may give the answer, I may give the actual voltage at the load, and you'll have to figure out how much power was transmitted. You have to reverse engineer it. Remember, that's the open circuit. And now we're going to talk about the specifics for the antenna that's L is equal to 0.485 lambda long. That's the antenna that we just were talking about with that example. So first thing I do, I want to know how much power is going to be received, and my load here is going to be just 50 ohms. And I want to know how much power is going to be received by that. So my open circuit voltage is the key first part. So V open circuit, and you only really need magnitude here. How do you get V open circuit? Right? Now remember, that is a half, the one I'm talking about is cut down to 0.485. So J, there is no reactive component. So I can say for the problem at hand, I can say the radiation resistance is about 72 ohms. Now, that'll vary a little bit. Yes, sir.
Since there's no reactive component, you wouldn't need that match, so
Yeah, hold it, no.
would you not?
That match only allows us to get the max, the open circuit voltage. Has nothing to do with the real load. This gives you the ideal amount of power that's possible to extract, assuming it's matched, will give us the maximum value of open circuit voltage. It's sort of like with Thevenin equivalent circuit.
Yeah.
First thing you had to do is find either the short circuit current or open circuit voltage, right? Has nothing to do with the load that will be attached to a Thevenin's equivalent circuit. Same here. So that's the radiation resistance. The open circuit voltage is this. So V open circuit, the square root of 4 times P received, 21.2 times 10 to the minus 9th, pardon me. And it's times the radiation resistance of the 0.485 dipole, which is 72 ohms. So could you give me V open circuit? 2.47 millivolts?
Yeah.
So here's my V open circuit. 2.47 times 10 to the minus 3rd volts. Now I put in, remember, I have to put in the antenna impedance next. All right, the antenna impedance, because it's cut down, is just 72 ohms, right? So this is 72 ohms, about. And remember, this stuff I'm showing you here, this is the internal model for the antenna. Now I attach my load of 50 ohms. And I'm going to ask for first, I'll ask for the voltage across the load. So what's the voltage across the load? Now this is pretty straightforward and simple. Isn't that just voltage division? So what would it be? What would be 50 over 50 plus 72, or 50 over what? 122 times 2.47 times 10 to the minus 3. Can you give that to me?
1.03 millivolts.
Millivolts, and that's P, by the way, right? Once you have that, the next thing I'm going to do, could we get current through there very easily? Divided by 50, right? The load. What about power in the load? This is power at the load or dissipated by the load. That's going to be what? 1/2 simply magnitude of the voltage at the load squared over 50, right? Agree, class? It's strict drill, isn't it, class?
10.3 nanowatts.
So it's just under half of the actual received power. Agreed? Now, the further away that load gets from the actual antenna impedance, the lower the percentage of power received. But remember, I made this really simple. There was no reactive component. Because if there was a reactive component, say it was an exact half-wave dipole, This would be 73.2 plus J 42.5. And you'd have to get the open circuit voltage. I mean, you get the open circuit voltage the same way. The radiation resistance would be 73.2, about the same. But then this current's going to be much more limited with that plus J 42.5, so you'd be able to deliver a lot less power. That's the point, okay? What I'm planning to do, because this is the one thing I'm planning to do, not right now, but later, is the arrays. Arrays are more involved, and theory takes me a full class period to go through array theory and show you how to do it. So what I'm going to do next is talk about radar. And it makes logical sense. Here it's freeze, one antenna, another antenna. Now we're going to have one antenna, launches power, hits an object, the object reflects power, comes back to the radar, and we figure out how much power is received, we figure out a lot of other stuff. Now with radar, I got to tell you one thing. There's a lot of aspects. The power received that we're going to talk about is only one aspect. There's a whole lot of other things that are involved with radar for identifying targets. The thing about radar is, it is very, very, you might say, complicated in the way it's done. There's signal processing, there's power received, there's all sorts of other factors you have to worry about. The atmospheric effects with the way the actual radar signal is slightly bent when it travels. There's an attenuated. It's a much more difficult problem than this makes it out to be. But this is a good starting point. So here's the thing. This is radar.
Radio detection and ranging.
That's fundamentally it. I mean, we can argue about some of this stuff. It's ranging and detection by radio waves is another way people, but it's really what he just said is the technical definition. It's just an abbreviation. You're using radio waves, that's the first radar, to detect signals because of echoes. So with radar, you have an antenna right here. And this is going to be a monostatic radar. And a monostatic radar means it uses the same antenna to transmit and receive. So we're only going to have one, well, actually, monostatic radar technically means the same point that the signal is transmitted from, it's received, but can use two different antennas. So for this one, there's the gain of the transmitter, and we'll assume that is the gain of the receiving antenna. Then you're going to have some range R that you're going to be at, and there's something out here, and we call this a target. Now the target has a certain electrical size. The electrical size is exactly likened to the aperture. It's in meters squared. It's called the radar cross-section. The radar's cross-section is in meters squared. And the symbol for the radar cross-section, oftentimes it's abbreviated RCS. The symbol is sigma, which I'm not crazy about, but you can call it sigma RCS. Because we use sigma for conductivity all the time, right?
So it's not an area though?
It is. It's meter squared. Always meter squared. So it's some electrical size of this thing, and I might add something too. The electrical size of anything is dependent on the aspect angles. For instance, if the frequency is high enough, there are many wavelengths over the feature sizes, then the electrical area is about the physical area if you look at it. All right, that's about the same. So if you look at this thing that way and you look at the area your eye perceives, it's much greater than looking at it this way. That's something that happens. Radar cross-section is a strong function of the orientation of the object if the object is not a sphere, or you might say an elliptical blob like an egg, then they're close. First thing we're going to do from this antenna, we're going to assume that we're transmitting a certain amount of power. I'll call it P transmitted. We're just giving that. And we say if we have the transmitted power, the next thing I want to do is find the actual average power density at the point where it strikes that target. To get the power density, this is just a basic antenna problem, isn't it? So I want the average power density striking that object. It would be simply the transmitted power divided by what? 4 pi r squared, right? The surface area of a sphere, 4 pi r squared. Now that's the isotropic power density. Now we have to multiply it by the gain of the transmitting antenna to talk about the focusing or the enhancement. So it's going to be the gain of the transmitter. Remember, the gain of the transmitter is a function of the angle. So I'm not even putting it there, but it has to be, I could if you want. It has to be a function of the angle that R makes with respect to the axis of the antenna if theta is measured from the axis. So that's the power density incident. Now the next thing that happens is the wave comes in, it strikes this, and then a whole bunch of power is going to be re-radiated. And the amount of power re-radiated has to do with the size, electrical size, or the RCS. Are you with me? So that's in watts per meter squared. Then we multiply it by sigma, and I'll put RCS. So now we have watts per meter squared times meter squared. That's watts. All that's re-radiated. And it is assumed it re-radiates like an isotropic wave. So now I take all this, and I divide it by 4 pi r squared. Take a moment, just think what I'm doing here. On the power density incident, then I find the total amount of power reflected. Think about the moon and the sun, all right? Find the intensity of electromagnetic radiation at the surface of the moon, multiply it by the cross-sectional area of the moon, and you get the amount of power that can be re-radiated in all sorts of directions. With me? Now, if I divide that by 4 pi r squared again, that's the amount of power density back here. Do you follow me on that? If you know how much power, think about it as re-reflected by the moon. If you want to know how much power is on the Earth, assuming it's isotropically reflected, it's not really, it's a hemisphere, not a full sphere, but you would divide that by 4 pi r squared, where r would be the distance from the moon to the Earth. Now that's the power density back here. Now that, what I've showed you, is the actual average power density back at the receiver, or at the transmitter. With me? That would be in watts per meter squared. Now I need to multiply by the aperture of the receiving antenna. Aperture is the electrical size. How do we get it? Lambda squared over 4 pi times the gain of the receiving antenna. And I'll put times gain of the receiving antenna. And I can make it a function of theta. Usually the gain of the receiving and gain of transmitting are the same. And the whole idea is with an antenna, the exact same pattern of transmission, the angular function that the power would weight the power transmitted, the gain, is the same exact thing you weight the actual ability to receive information. It's a reciprocity kind of problem. So this gain here is the gain of the receiving antenna, as if it was transmitting. Now what you have is the total power received, and I put PF here, but now this whole thing is P received, and this is true. And I'm going to go ahead in a second, and I'm going to reduce this, because this is the way, what I'm about to show you is called the radar range equation, and it is the most common form of the radar equation most people are first introduced to, and it's just relative to the power transmitted and received. So here, we take the ratio of P received over P transmit. Remember before when we did Friis, that was a one-way link from a transmitter to an antenna, right? Here, it's going back, bang, hits something, comes back. So for this one, it's always proportional. If you look at this, the gain of the transmitter times gain of the receiver. They're usually the same. Then it's proportional to lambda squared, the lambda squared here, and it's proportional to the size of the object, the electrical size of the object you're striking. It's also divided by 4 pi cubed. You can see 4 pi, 4 pi, 4 pi. Then it's divided by r to the fourth. And this is the standard, it's called the radar range equation, RRE. And that tells you the amount of power received for a given amount of power transmitted. A couple things happen too with this equation I'm going to tell you. With radar, you're not just looking for the amount of power received, it's the time delay. You send a signal, it goes out, it strikes something, and it comes back. We're assuming we're in the atmosphere or in free space. It's moving at the speed of light, right? Agreed? Everyone? So if that's the case, when we talk about the time delay, if we look at this, the delta t that the signal would take to go out and back, well, it goes 2r away, right? And it's limited by c, so that would be the time it takes for the signal to get back. And usually, if you were doing this real simple, this is like the very first British radar that they used with the radar fence around England during World War II. So they send a signal here, and this would be a big pulse right here. It'll have a short duration, so this is P transmit. And what I'm going to show you, this would be logarithmically here, logarithmic power axis. Then they wait, and all of a sudden they get an echo, and they see this little blip. And they can figure out, if they know the time delay, they can estimate the range to the target. There's a lot more than what I'm telling you about this, but they can estimate the range, simple. And you've heard echoes before, right? In canyons or wherever. The echo, if you knew the speed of sound, you could estimate how far away the object was that you got the echo from. That's how bats and dolphins do echolocation. And they have their own form of sonar, which is basically the same thing as radar, with one exception. With radar, it's the speed of light limit. With sonar, it's the speed of sound in the environment, which is orders of magnitude less. Maybe 5, 6 orders of magnitude less. I'm going to give you problems. I think you can handle the theory that I just showed you pretty well. It's straightforward, but please do these problems. Test is next Friday. On Friday, I plan to do array theory online. I'll give you the references. You'll get a Zoom link from me. Wednesday, what I'm planning on doing in this class is sort of a review. I'll cover the questions and problems given on Monday, but do a review for the test on Friday. How many want a quiz Monday? I don't think we're going to have a quiz Monday. I'm going to warn you about one thing. On the exam, I will give you things like the transmission line input impedance. I'll give you the gain for an exact half-wave dipole. I'll give you some information like that, and for the loop antenna, I'd give you the radiation resistance and stuff like that. But I'm not going to give you all the formulas you see. You got to know how to use them, got to know what they mean. And I would be sure I understood how to do the problems assigned and the quizzes. Monopoles are covered. If you haven't done that stuff, do it. Whatever you haven't done, start doing it now, because it's cumulative. Last thing I'm going to tell you is all my tests are created based on the homework/quizzes. None of them are out of the blue. I don't do anything where I don't have a quiz or a homework problem that I looked at and modified. Sometimes I give the exact same thing. So I'm telling you that now. You guys have test week next week. Please make adjustments in your schedule. Get the studying done. Don't wait. And for heaven's sakes, the night before the test, get a good night's sleep. That is the single best thing you can do for yourself.